Hello everyone, my name is Martin and I'm going to present our paper towards efficient shape analysis with tree automata. Shape analysis deals with reasoning about dynamic data structures and therefore it needs a domain to represent them. We propose a domain based on 3D compositions with graphs with bounded tree width, which is expressive, it's efficient, there are efficient algorithms for the domain, and also have the following properties not described in the paper, and that's the ability to learn abstractions of inductive invariance and reason locally about local changes in code. It's based on our previous work on forest automata, and this work is still in progress, which I will mention later. Let's introduce 3D compositions. Here is a formal definition, but I will try to give you an intuition. So consider this graph of circular double-linked list. And here are two of its 3D compositions. The nodes of the compositions are called so-called bags, where variables represent nodes in the original graph. So variable v represents the first node, the variable x the second node, the y the third node, and the variable z the last node. Each variable has its scope, which is defined by parameter assignments on the edges. Parameter assignments forms pipes, and the pipes are here shown by this colored line. So red pipe represents scope of V, the green pipe the scope of X, and so on. As we can see, the red pipe starts in the first bag because the first occurrences of V is here and ends in the last bag where is the last reference to V. The pipe X, the green pipe starts in the first node where is the first occurrence of X and ends in the third node where is the last reference to X. The second decomposition here differs from the first one because it was unfolded from the second node of the graph using a previous and next pointer. And we want to be able to derive one decomposition from another's, and we need two operations to be able to do that. And I will show you how to transform this right decomposition to the left one using these operations. The first operation is reconnection, which takes two bags, B0 and B0 prime, and basically connects B0 under the B0 prime. Here the bag Z is connected under below the bag Y, which results to this decomposition. And we also need to prime variables in parameter assignments to prevent inference of pipes along the reconnection path with pipes in the rest of tree. Here is no rest of tree because it's simple graph, but in more complex cases it may happen, and therefore we need priming variables in each operation. The second operation is rotation, which takes two bags, B1 and B1 prime, and inverts the path between them. Here the path consists of one edge, and we can see that this edge leading from X to V after the rotation leads from V to X. And again, we need to prime variables. Finally, we get the 3D composition, which is the same as the left one on the second slide. And having these operations, we can formulate our main results. So let's start with so-called phase, which is a set of operations that could be performed at once. Then one phase at most double the number of variables. The first conjecture is that an equivalent decomposition T prime can be obtained from T in a number of phases that depends only on maximum tree width of T or T prime. 3D compositions can be represented also as language of tree automaton, and we can add up dimension operations to tree automata. Then we get the second conjecture, which says that tree automata phase at most doubles the number of variables and leads to an automaton that is of polynomial size, assuming fixed tree width of the original automaton. And this automata inclusion is as time complete. Conjectures 1 and 2 give entirement, which is singly exponential. That's the main result we want to prove. We haven't proved it yet. We haven't proved the conjectures and lemma. but is the main target of our future work. And that's all. Thank you for your attention.